So we're on to what might be the last functional group. I've already kind of mentioned carboxylic acids. It was in the last little part of the lesson where I was talking about an increase in oxidation, and that's exactly what a carboxylic acid and an ester are. In our functional group, we now have the carbonyl group that is now connected also to an O. So it's like we've added an O onto an aldehyde. It's like we've taken an aldehyde, which just had the C double bond O, and then an H on it, and it's like we've stuck another O in there. And that's exactly what we've done. When we go to the point where we're talking about creating carboxylic acids, we're going to mildly oxidize an aldehyde. We're going to stick an O into it. When we add an oxygen to the carbonyl group, it becomes a carboxyl group. So we've got, again, that oxy in there, kind of like our methoxy, right? As soon as we add that oxygen in there, they like to stick in that little part of oxy. So this is a carboxyl group. You can think of a carboxyl group as being made up of an alcohol stuck to a carbonyl group. A carboxylic acid has to have the H on the end of it, and therefore there's going to be no number needed when we start naming it, because it's always going to be on the end. Looking at its properties, that end is definitely polar because it's got the C double bond O. That's going to be unequal sharing, but it also has an OH, and therefore it can undergo hydrogen bonding. So this is even more polar because part of the molecule can undergo dipole-dipole interactions, and part of the molecule can undergo hydrogen bonding interactions. So when we take a look at the properties, off to the side greater than alcohols is carboxylic acid. So we've now added our carboxylic acids to that side, and they can undergo, and if you wanted to put a title, remember we were putting some titles on these. These guys have London, right? They have dip-dip, and they also have H bonding. Now in the past I've said to you, don't put dip-dip and H bonding because they're two different things, right? If I'm talking about something like water, right? Some people will say, what do I put there for the type of intermolecular force? Can I put dip-dip and H bonding? And I'd say no, this is just H bonding. But in this molecule here, there is a dipole part of it, of the molecule, and an H bonding part of the molecule. Because it's a larger, more complex molecule, it has both of those interactions existing within the same molecule. With this one, it's just H bonding, okay? All right. So naming carboxylic acids, I've just given you the sheet on it. It's very much like aldehydes because the parent chain has got to end or start with that C double bond O, OH. No number is needed. We don't need to tell it where it is. The ending of the name, the suffix, instead of al for the aldehyde, is oic acid, right? Oic acid. It's a funny one, but these are all acids because that H on the O easily falls off, right? We've seen acetic acid, right? Acetic acid is actually ethanoic acid, and the H falls off very easily on all of these molecules, and that's why they're called acids. Let's just first go over some of these. Methanoic acid is the simplest one. That's simply C double bond O, OH, and it's got an H on it. Methanoic acid. And that C double bond O, OH, that, as you go on in chemistry, will be the cue that when you read it, oh, that's a carboxylic acid. So here we've got ethanoic acid. That's vinegar. That's acetic acid, basically. CH3, C double bond O, OH. All right? So if you had something like hexanoic acid. Look, I've got the same thing twice. Why do you think I have that? That's the craziest thing in the world. Anyway, hexanoic acid. 1, 2, 3, 4, 5, 6, and double bond OH. Bang. I always put it on the end. I don't know why. And that's maybe because of the way the naming goes, hexanoic acid, so I just put that on the end. Doesn't matter. That's, by the way, the number 1 carbon, though. If we have a branched situation, that's a number 1 carbon. H3, H2, 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 and then that's full. All right, benzoic acid. Benzene, and then C, double bond OH. That's a terrible double bond O up there, by the way, folks. It looks like a, I don't know what it looks like, a little guy standing on the carbon. But that's a C double bond OH. Okay, so here I've got a couple of others that are a little more complicated. And what have I done with this? What did I do here? That's the wrong, have I changed it on that? Oh, and I didn't fix it. That's terrible. So I got to do a little change on this. It's not a big deal. I must have used the same one. This has got to be gone, and that's got to be an H. All right? And you know what? That's kind of silly because look at this. This is my benzene ring, and I've just drawn it. And so what is this guy? We just did that. What is that called? Benzoic acid. The reason things are looking disheveled is that I'm slowly transferring things to some of these practice pages, and obviously I rushed through this and didn't do any proofreading. Let's take a look at this one, though. That's a good one to check. So here we've got the carboxylic acid group on the end. That makes it a carboxylic acid. Now I'm putting the branches on it. 1, 2, 3, 4, 5, but I don't know how to name that funny thing. 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. It doesn't make any difference, but that has to be 1. 1, 2, 3, 4, and I'll put the 5 over here with a branch there and a branch there. So main chain is 5. It's got a carboxylic acid on the end of it. So what's the main name called? Yep. Pentanoic acid. Pentanoic, and then it's actually 2 words, but acid. Pentanoic acid. Now I do my branches. What's first? 3-ethyl, right? E. 3-ethyl, and then 4. Oh, and I'm in big trouble. Methyl, and you know the way it works. Snake back over there. So the chain is defined by that oic acid on the end. You start it at number 1. You label it up as you normally would. So if I'm drawing 2-methylbutanoic acid, I'm looking at the end like I always do. 1, 2, 3, 4. I always put that double bond OH on the end. But the trick with that is that becomes my number 1 carbon, so I work my way backwards. So 2-methyl puts the CH3 on that guy. Because I have to work my way backwards, because I always draw it that way. You could flip it around if you'd like. Doesn't make any difference. And then H3, H2, I need an H on that guy, and we're done. As I've already mentioned, controlled oxidation means carefully increasing the connections of a carbon, and in this case we call it the key carbon, right? That carbon that's connected to the alcohol. As we continue to control the oxidation, we want to increase those connections of that key carbon with oxygen. And that's all we need to do. We need to take that aldehyde, again do another controlled oxidation, and turn it from the aldehyde now into the carboxylic acid. I'm showing this as a series of reactions because many of the problems that an organic chemist has to deal with is multiple step reactions. So we're going to do this as a multiple step reaction. We've already seen the reaction of a primary alcohol with oxygen. That was the beginning of this lesson. This oxygen, take an H from here and an H from here and turn it into water, and we'll have a double bond formed in there. And we get CH3 C now turned into a double bond, and then an H. We've turned our ethanol into, and this isn't a carboxylic acid yet because it doesn't have an oxygen in there. What's this called? Ethanal. Yeah, ethanal. We've turned our ethanol into ethanal. All right? Now comes the second step. Now I'm going to take the ethanal, CH3, CH, double bond O, and we're going to continue to oxidize it. In this case, there isn't any H's or anything taken off. This O is literally added in between the C and the H. It's added into that position. And that gets CH3, C, double bond O, and now we have an OH. And what is this stuff called? Ethanoic acid. Ethanoic acid. So it's a two-stepper from the alcohol. Let me just give you this last little statement here to finish this.